Welcome to P. Clark Calc, Practical Calculus for the Busy Math Student. And here we're going to take a look at the infinite series remainder formula, which is used to calculate how good our estimates are of infinite series sums using finite series sums or partial sums. In this question, we are posed with a problem of trying to come up with an estimate of an infinite series sum. We've seen a couple of cases where we can actually calculate the exact value, like a geometric or the telescopic cases, but a lot of times that can be pretty difficult to actually come up with the exact value. So what we do is we come up with an estimate using a partial sum. And so here we're going to estimate using S sub 5, that means the sum using the first 5 terms. And we know it's going to be convergent by the integral test. The integral test states that if the corresponding improper integral is convergent, then the infinite series is convergent. And we have this special case of the integral test, a nice thing called the p-series test. We look at that and we say, well, p is equal to 2 in the denominator, and p-series says anytime p is greater than 1, we can state that that is convergent. But the only reason we can state the p-series is the integral test, so it's basically a corollary of the integral test. So we know that this does have a numeric value, but how do we approximate it? So in this exercise we say, well, let's look at S sub 5. S sub 5, also known as the summation of 1 over n squared from 1 to 5, which we can do that explicitly, so we just write that out. That states that S sub 5 is equal to 1 over 1 squared plus 1 over 2 squared, so 1/4, 1 over 3 squared, 1 over 4 squared, and 1 over 5 squared. We could have some fun and go and find the fractional value of that, but let's not do that right now. If you evaluate all those and add them up, the partial sum is 1.46361 repeating. So one thing's for sure, we know that that is something that's less than the infinite series sum, because there are a number of terms, right, infinitely many, that are out there that we've not added up. One thing we should point out as we move ahead here and try to figure out how close we are with our estimate is that when we talk about the integral test in convergence, it's a qualitative test. It states, well, if the integral is convergent, a series is. If the integral is divergent, a series is. But it doesn't allow us to find a numeric value. And sometimes students make the error of assuming that if you have a convergent case, that the infinite integral provides the sum of the infinite series, which is definitely not true. However, they are really closely related, and it all ties together in this series remainder formula. So let's take a look at that. So at this point, we've defined the partial sum as about 1.46361, and what that is really, and you think about what is a series sum, we can think of it as a Riemann sum. Because each of these rectangles with a width of 1 has a height that's defined by each of the first terms of this series. So this first rectangle is 1 over 1. The height of that is 1. The second one is 1/4. And so on. So anytime we're talking about the sum of a series, we can envision it as a right-sided Riemann sum, and the sums of these areas of these rectangles is what gave us our partial sum S sub 5 value that we learned previously. So what the remainder of a partial sum is defined by this formula, and we use R sub n to define the remainder. What the remainder is the improper integral from n to infinity. And if you look at what the formula says here, it states that the actual series sum that we're trying to determine lies somewhere in between our partial sum that we just calculated, somewhere above S sub 5, and somewhere below S sub 5 plus the improper integral from 5 to infinity. And if we look at our graph here, this function This continuous function is the corresponding function 1 over x squared, which we know is convergent. And we're going to calculate the area under that curve from 5, in this case n, to infinity. And so if we look at the graph, we can see why the remainder formula works here, because our right-handed Riemann sum, which is the sum of the terms of the series, is always going to be inscribed, because in order to be convergent here, we have to have a positive monotonic decreasing series. So that means that these right Riemann sums are going to be inscribed, and they're always going to be less than the corresponding improper integral. So that's why it works. Once you understand that, it's just a matter of being able to do the improper integral, which we can do that now. And we call this r sub 5. And that's simply going to be the integral from 5 to infinity of 1 over x squared dx. Remember, we use the x variable in the integral. We're talking about the continuous function, as opposed to n when we're talking about the discrete function, the function of the natural numbers. But they're corresponding with each other, and we can do the integral with 1 over x squared, which ends up being negative 1 over x. And at this point in our calc lives, we've kind of mostly ditched the formal limit notation when we're doing our improper integrals to infinity. We just understand that infinity is not a number. We can't really plug it in, if you want to call it that, but we're taking the limit as we approach infinity, which for negative 1 over x is 0. And then we have minus a negative 1/5. So our remainder, r sub 5, our maximum possible error on our estimate, is 1/5. And so if we take that and apply it to our formula, what it's saying now is that my actual sum, the one that I was trying to calculate, which is 1 to infinity of 1 over n squared, must lie somewhere between s sub 5, 1.46361 we'll call that, and s sub 5 plus r sub 5, which would just be s sub 5 plus 0.2, 1.66361. And so we have a reasonably good estimate at that point. Obviously, if we wanted a better estimate, we could use more terms. It would just be a matter of how accurate do we need this to be. So there it is. It's an interesting and practical formula. It lets us calculate how accurate our partial sum estimates are of infinite series sums, which cannot be determined exactly. If you want to learn more about infinite series or calculus in general, you can find those on my calculus books, available for a nice price on Amazon. Until next time, I'm P. Clark.